Everyone, welcome to the chemistry channel. So today we're going to be talking about electron affinity. So what is electron affinity? Well, electron affinity is defined as the change in energy, so this means the change in energy associated with adding an electron to a neutral atom in the gas state, or the change in energy associated with an anion. Remember, an anion is a negatively charged atom losing an electron in the gas state. So therefore, electron affinity can be expressed in two different ways. So let's do the first way. Now the first way is when we add an electron to a neutral atom. So this can be symbolized by this chemical equation. So you have your neutral atom in the gaseous state, and we add an electron to that atom, forming our anion. And this is the first way that you can express electron affinity. Now, the change in energy associated with this process is negative. So the change in energy is generally going to be negative. And that's because we are forming a new interaction between an electron and a nucleus, which causes a release of energy. So therefore, this process, the first process, is exothermic. Now the second way is when we cause an anion to lose an electron in the gas state. And we can express this as the reverse of the first one. So we start with our anion, and we show it decomposing into the neutral atom and its electron. Now this process is positive, it has a positive change in energy, and it is endothermic. Now note that the magnitude of delta E is the same for both processes. However, the only thing that differs is the sign of energy. So we can express this notation as, so note that the change in energy associated with process 2 is equal to the negative of the change in energy associated with process 1. And that's because you are just reversing the reaction, so we just change the sign. And remember that endothermic is when you take in energy or take in heat, and exothermic is when you give off energy or give off heat. So the common way to express electron affinity is with number 2. So chemists will often use number 2 where you take an anion and decompose it in order to express values of electron affinity. And we'll get more into this later in the video. So now let's talk about the trends of electron affinity. So the trends of electron affinity. So imagine that you have a positive 1 nucleus and a positive 2 charged nucleus. Now, which nucleus do you think will be easier to add an electron to? Hopefully you said the positive 2 charged nucleus. And an electron would be easier to add to the positive 2 charged nucleus because it has a greater positive charge. So it is easier to add an electron to an atom with the positive 2 nucleus because the nucleus exerts a greater force of attraction on the electron. So you may remember that we can express this force of attraction by Coulomb's law. So Coulomb's law is equal to a constant times the product of two charges over the distance squared between the two species. So as we increase the charge of the nucleus, there's a greater force of attraction. So therefore, we can extend this to effective nuclear charge. As the effective nuclear charge of the atom increases, in general, we'll see that there are exceptions to this, the easier it is to add an electron to a neutral atom, and the harder it is, and the more difficult it is to remove an electron from an anion. So therefore, as the effective nuclear charge increases, it is in general easier to add an electron to a neutral atom and more difficult to remove an electron from an anion. So what do I mean by easier? So what am I talking about when I'm saying easier? When it is, why is it easier? What does it mean to add an electron in an easier fashion? So in order to do this, we have to bring back change in energy. So recall that the change in energy associated with adding an electron or losing an electron can be positive or negative. And this positive and negative tells a lot about how easy it is to gain or lose an electron. So what does it mean when the change in energy is positive? Well, when the change in energy is positive, so when delta E is positive, the products are higher in energy than the reactants. So why is that so significant? Well, this tells us that the products, so this means the products, have more energy than the reactants. So this means the reactants. So if the products have more energy than the reactants, this means that the product are more unstable than the reactants. So when the products are higher in energy than the reactants, the products are more unstable. So therefore, when your products are more unstable than your reactants, that reaction is unfavorable to move forward. So what about when the change in energy is negative? What does this mean? Well, when the change in energy is negative, it's the opposite. So when delta E is negative, the products are lower in energy than the reactants. So this means that the reactants are more unstable than the products. So when your delta E is negative, this tells us that the reactants are more energy than the products. So therefore, the products are more stable than the reactants. This means that the reaction will want to move forward. So in order to understand this, I have an example. So here we have the process of adding and losing an electron on an oxygen atom. So this part shows us, this number one shows us adding an electron to oxygen, forming the oxyanion, and it also shows us the change in energy associated with this process. So this change in energy is equal to the electron affinity. So this change in energy is equal to the electron affinity associated with this process. So this process right here, when you add an electron to the neutral oxygen atom, has a negative delta E. So what is this telling us? So delta E is negative for this process, and this means that the oxygen gas, the negatively charged oxygen gas, is more stable than the neutral oxygen. So this is the reactant. And therefore, oxygen wants to add an electron to itself. So this negative delta E is telling us that oxygen wants to add an electron. So what if we were to reverse the process, where we remove an electron from the oxyanion? Well, you would get the same magnitude of electron affinity, or the change in energy, but a different sign. And what is this telling us? This tells us that the oxyanion, so the negatively charged oxygen atom, wants to keep its electron. And it wants to keep its electron because the oxygen gas, the neutral oxygen gas, is less stable than the oxyanion. So therefore, the oxygen wants to keep this electron. So these two things, these two ways of expressing electron affinity, are telling us the same thing. So they tell us the same message. And that message is that oxygen really wants to gain an electron, and it doesn't want to lose it. So it's basically telling us the same thing. It's telling us that oxygen wants an electron and wants to keep that electron. So these two processes are just two different ways to tell us the same thing. So therefore, there are 4 general rules that you should know about electron affinity. So the first rule is when you have a neutral atom gaining an electron to form a negatively charged, or the anion form of the atom. So when this form of electron affinity has a negative change in energy, the atom wants to add the electron. So it wants to add the electron. So let's get rid of this circle. Sorry about that. So when this form of electron affinity, so when you are adding an electron to a neutral species, has a negative electron affinity, so the change in energy is electron affinity. So when it has a negative electron affinity, the atom wants to add the electron. However, when this form of electron affinity, so when you're adding an electron to the neutral atom, has a positive delta E or positive electron affinity, the atom does not want to add an electron. So when you have a positive delta E, the atom does not want to add an electron to it. So now let's look at the other process. So where you have an so when you have an anion decomposing into its neutral atom and its electron. So when this process has a positive delta E, the atom wants to keep its electron. And that's because when it has a positive delta E or a positive electron affinity, the product is more unstable than the reactant, therefore it wants to keep its electron. However, when this process has a negative delta E, the atom wants to get rid of its electron. So when it has a negative delta E, it wants to get rid of its electron. So those are the 4 general rules that you need to know. So it's important to note that chemists generally use this decomposition form in order to describe the trends of electron affinity. So this means electron affinity. So the chemists in textbooks tend to use this form of electron affinity in order to describe the trends associated with it. So the thing to know is that as delta E increases for this process, so as delta E increases, the more an atom wants to keep its electron. So as delta E increases, the more an atom wants to keep its electron. And this is the important form of electron affinity that you need to know in order to describe the trends associated with it on the periodic table. So using what we learned up here, we can now describe the general trends associated with electron affinity on the periodic table. So as we go from left to right, electron affinity increases in general. And as we go from bottom to top, electron affinity tends to increase as well. However, as we go from right to left, electron affinity tends to decrease. So let's actually change that, sorry. So electron affinity tends to decrease as we move from right to left. And as we go from top down, electron affinity tends to decrease as well. So what is this telling us? Well, it's telling us that it gets more difficult to lose an electron from the corresponding anions as we move left to right and bottom to top on the periodic table in general. So this is only in general, and there are actually a ton of exceptions associated with electron affinity. And we're going to go through each and every exception and explain why they are the way they are. So the first exception to this trend is when you move from the halogens to the noble gases. So what would you expect as you move from the halogens to the noble gases? What would you expect in electron affinity values? You'd expect that the electron affinity would increase from halogens to the noble gases, according to this trend. However, this is not the case. Instead of increasing, they actually decrease. And I have here an example with chlorine and argon. Now, chlorine is to the left of argon, and they're in the same period, and chlorine is, of course, a halogen, and argon is a noble gas. So chlorine has an electron affinity value equal to plus 349 kilojoules per mole, while argon has a negative electron affinity value. So this is telling us that the electron affinity has decreased as we moved from left to right. So why is this the case? So let's clear up what this is saying here. So argon wants to lose its electron, while chlorine wants to keep it. Wants to keep its electron. So why is this the case? Well, in order to do this, let's actually write an orbital diagram. So let's draw the orbital diagram for the chloride ion and the argon anion. So let's draw our orbitals. So we start off with our 1s, and we have 2 electrons there. 2s, 2 electrons there. And then 2p is just above that. So our 2p is fully filled. Then the 3s, and then our 3p. So then we have our 3p, which will be fully filled. So now let's move to our argon. So our argon will have pretty much the same orbital diagram except for one little electron. So let's draw our orbital diagram for the argon anion. So then our 3s, then our 3p, and then our 4s, our one lonely electron in the 4s subshell. So this chloride ion has the electron configuration. So this is the electron configuration of argon. And argon is a noble gas. So this means noble gas. And noble gas electron configurations are very stable. So this is a very stable configuration. However, argon has this argon anion with the extra electron has broken the noble gas electron configuration, and the electron, the added electron, is in a higher energy level. Therefore, this electron is very easy to lose. And argon wants to go back to its noble gas configuration. So therefore, it does not want to keep this electron, and it wants to go back to its noble gas configuration. And that is why noble gases have lower electron affinity values than halogens. So that is the first exception. So the second exception is actually seen with group 1A to group 2A. And remember that group 1A is the alkali metals and group 2A is the alkali earth metals. So in order to illustrate this exception, I'm using lithium and beryllium. So the electron affinity associated with the lithium is plus 60 kilojoules per mole, while the electron affinity associated with beryllium is negative. So why is this the case? Why is beryllium, which is to the right of lithium, why does beryllium have a negative electron affinity while lithium has a positive electron affinity? Now, in order to describe this behavior, we have to use a orbital diagram again. So we're going to use the orbital diagram again. So let's fill the orbital diagram for the lithium anion. So the lithium anion first fills in its 1s subshell, and then the 2s subshell. So now let's go to the 2p. Let's go to the beryllium atom now. So the beryllium anion has electrons in its 1s subshell, its 2s subshell, and then one lonely electron in the 2p subshell. So why do you think it's easier to lose an electron from beryllium than it is to lose one from lithium? Well, it's because this electron is in a higher energy subshell. So it is much easier to lose this electron than it is to lose an electron from the 2s subshell, because this electron is more unstable than the electrons in the 2s subshell. Therefore, it's much easier to lose the electron in this 2p subshell because it's higher in energy. So the electron is in a higher energy subshell than the 2s subshell, making it easier to lose. And that's why beryllium and the group 2A metals have a lower electron affinity than the group 1A. So the third exception is seen with group 4A to group 5A. And group 5A has a lower electron affinity than group 4A, which is opposite to what we would expect based on our general trends. So in order to show this, I use carbon and nitrogen. So the electron affinity associated with carbon is 122 kilojoules per mole, while the electron affinity associated with nitrogen is negative. So in order to understand this, we have to bring out our orbital diagrams again. So let's fill out the electron configuration of the carb anion here. So we have 2 electrons in our 1s, 2 electrons in our 2s, and 3 electrons in our 2p. And note here that we are obeying Hund's rule and that we are maximizing spin, causing us to have the lowest energy configuration. So now let's go into our nitrogen anion. So let's go into our 1s, so we have 2 electrons in there, 2s with 2 electrons in there, and then our 2p subshell with 1, 2, 3, 4. Now note that this nitrogen anion has a much lower electron affinity than the carb anion here. And why is this? Well, it all has to do with this extra electron in this particular orbital here. Now, this electron here is right next to another electron in this orbital. This means that we have greater electron repulsion in the 2p subshell in this species than in the carbanion. So therefore, it's much easier to lose that electron than it is to lose the electron in the carb anion. So therefore, the group 5a atoms and group 5a elements have a lower electron affinity than the group 4a. So then the last exception is seen with when we go from period 3 to period 2. Now we would expect going from period 3 to period 2 that our electron affinity would increase. However, this is again not the case. So here I use the electron affinities associated with chloride and fluoride. So the electron affinity associated with chloride is plus 349 kilojoules per mole, and the electron affinity associated with fluoride is plus 328 kilojoules per mole. So why is this the case? Why is the electron affinity associated with fluoride, which is in period 2, less than the electron affinity associated with chloride, which is in period 3? Well, it actually has to do with the size of the atoms. So because the atoms in period 2 are much smaller than the atoms in period 3, the electrons in period 2 atoms are easier to lose than electrons in period 3 atoms due to electron repulsions. So because the period 2 atoms are much smaller than the period 3, you have much greater electron repulsions, which means that period 2 atoms, period 2 atom electrons are much easier to lose than period 3. So that is why the electron affinity of period 2 atoms are a little bit smaller than the electron affinities of period 3. And that is it for electron affinity. So electron affinity is a lot more confusing than ionization. So with that, I thank all of you for watching, and I hope I helped you all understand this material a little bit better, and I hope to see you all next time. See you around, and good luck, everyone.